Okay, can you see that?
Yep.
Perfect. All right. So, um, the important thing that we're getting to is that not all languages are regular, right? So we've been doing regular languages for a super long time. And now we want to look at languages that are not regular. We're going to prove that in the next lecture, but right now we're just starting with this weird party trick, right? And I said, suppose you have some DFA. This DFA only has um, three states, and pretend that this last state is a double circle, and the first state is the start state. And if I have to go, if I have the string that takes me boom, boom, and ends up at the accept state, yeah.
Yeah.
How many letters are there? How many booms did I just do? One, two, right? So there's two,
Yep.
right? So you've got to visit three states, but there's only two letters in the string, right?
Yep.
But you have to visit three states to accept. Yeah.
Yep.
Um, so if I visit three states, I have two letters. What happens if I have four states? How many letters do you think I have to see? So
Three.
got it, right? Four states, three letters. 27 states, 26 letters. Yeah.
Yep.
Okay. So, and then I'm flipping it around. So before I was saying 27 states, 26 letters. Now I want to say if I have 17 letters, that means that it has to visit 18 states, right?
Okay.
Because it's got to go the other way. Does that make sense?
Yeah.
Right. So if it has two letters, visits three states, three letters, visits four states, 26 letters, 27 states. So now I just flip the chart around,
Okay.
right?
Yeah.
So 17 would be 18 states, right? Because it has to start and then go boom, 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 boom. So there's always sort of the start and end, right? So if we look at the three again, started here, right? And I went two jumps, but to do two jumps, there's a start and an end, right?
Hmm.
Does that make sense?
Yeah.
Okay, cool. All right. Now, the important part about this is we visit that many states, but it might be that there's a loop in there, right? So, for example, if I have the string A, B, B, A, it could be A, B, B, A, right? Or it could be A, B, B, A, depending on if I have a different DFA, right? But all I'm trying to show here is just because I say you visit four states, it could be that there's like a double, like
Okay.
A, B, and a loop, right?
Yeah.
Makes sense?
Yep.
Okay. And I am admittedly going through this a little bit fast because this is like an hour and 15-minute lecture, and I think we
Yeah,
want to
it's okay.
talk about stuff after that. But okay. So what I'm trying to do now is remember the big picture is we want to prove that some languages aren't regular, and I'm trying to give you an idea of how we're able to do that. So I'm going to give you a concrete example. I'm going to pick a DFA that has five states, but that recognizes an infinite language. Okay. So, and if it has loops, it has to recognize an infinite language, right? So there's five states, one, two, three, four, five. But like this accepts ABA, right? You got to say yeah or something. You're
Yeah.
blinking.
Yeah, I got it. Yep.
It accepts ABA, but it also accepts BBBB ABA or 50 Bs ABA or 10,000 Bs ABA. And then there's also all these extra loops in there. So this is an infinite language. Yeah.
Okay. Yep.
Because we can put as many Bs in there as we want. You agree?
Yeah, I got it.
Okay. You can also give me thumbs up if you don't want to have audio on here. I just need to
Okay.
know.
I
Okay.
got
All right. So if I pick a string that has five symbols in it, right?
you. Yep.
And it's accepted by this DFA, it's got to do six visits because of the whole, you have to have a start and an end in the middle. So
Okay.
there's got to be so since there's six visits, at least one of these states gets repeated. So I think I have an example here. Oh no, first I have to tell you pigeonhole principle. Probably learned pigeonhole principle in discrete, but basics of the pigeonhole principle, if I have 10 pigeons and I only have nine holes for them, somewhere there's going to be two pigeons in one of the holes if I need to put the pigeons in the holes,
Okay.
right?
Yep.
And in fact, I think my theory is pigeonhole principle came from the fact that in fact in the UK they call these mailbox things pigeonholes, right? So if you have 27 pigeonholes and 28 flyers, and whoever is putting the flyers into the mailboxes um, needs to get rid of all the flyers, somebody's going to get two. That
Okay.
makes sense.
Yeah.
Okay. But so we can say by the pigeonhole principle, if I have A, B, C, B, A, that's 5 letters, right?
Yeah.
And I only have 5 states. But we know if we have 5 letters, we have to do sort of boom, 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 boom. Uh, I'm going to call it 5. Sorry, 1, 2, 3, 4, 5. Yeah. 5 booms, 5 transitions, right?
Mm-hmm.
And each transition has a before and after. We know that we're going to have something is repeating, right? So in this case, A, B, C, B, A. Yeah.
Okay.
Because I have to visit 6 states and there's only 5 of them. So something has to repeat. And in this case, I'm doing, I'm actually repeating 2 of them, right? So I'm going from 1 to 2 to 3, back to 2 to 3 to 4. Oops, sorry, before I accept this thing. So do you see how
Yeah.
5 letters? So if I go back to the picture again, when I had 2 letters, oops,
Yeah.
I had to visit 3 because like you have to have somewhere you start and then you do 1, 2.
Okay.
For real, okay?
Yeah. Yeah. I got
Maybe
it.
I'm rushing this, right?
Yeah.
But so it means that if I tell you that I have a 5 letter string that I'm accepting, yeah,
Yeah. It has to visit 6 states.
it has to visit 6 states because it's got to start and then visit 5 more, right?
Mm-hmm.
And so if it's going to start and visit 5 more, it's got to visit 6. There's only 5 of them. So there's got to be at least one repeat. In this case, there's two because A, B, C, B, A. So it went to 2 and 3 twice.
Okay.
For real, okay?
Yeah.
Okay. All right. So I picked a DFA with 5 states for an infinite language. Um, and I picked a string that has at least 5 symbols, excuse me, accepted by this DFA, which meant that there had to be some state had to be visited twice. Okay.
Mm-hmm.
And what I'm going to do, and this is a little bit weird, but what I'm going to do is I am going to now choose to split up the string based on how the repeats happen. And don't worry about why I'm doing this weird thing. Just say, yeah, okay, fine. I see what you're doing.
All right.
So I had the A, B, C, B, A thing, right?
Yeah.
And I started at state 1. I saw the A, and then I ended up at state 2, right?
Yep.
And then I saw the B and I ended up at state 3. I saw the C and I went back to 2, right? Do I have, yeah, here we go.
Yeah.
I saw the C, I went back to 2. I saw the B, I went back to 3. A, I went back to 4, right?
Okay.
You understand what I mean by the visited?
Yeah. Yeah. I get it.
Okay, cool. So what's the first state we visited twice? We visited 1, then 2, then 3, then 2, then 3, then 4. So what's the first state we sort of revisited?
2.
Got it. Correct. Okay. And what we're going to do is I'm going to draw a line through the first repeat
Okay.
just for fun. No good reason why from your perspective, except do you understand what we did? We looked at what states it visited, right?
Yeah.
We said, what's the repeat? We circled just the first repeat. And then I drew a line through it.
Okay.
Okay.
Yep.
All right. And now when I do that, I end up with 3 sections. Okay. There's before the first line, in between the lines, and after the first line or after the last line. Yeah.
Yeah.
Okay, cool. So I'm going to call this first piece X, the second piece Y, and the third piece Z for no good reason except I decided to do it.
All right.
Okay.
Yep.
All right. So here's my question. Look at the DFA. If I got rid of the Y part, so I get rid of BC, is this string, so it would be A, skip the BC, BA, is that accepted by this DFA?
No.
Well, hang on a minute. What happens if I do
Wait,
A, BA?
A,
A,
yeah, it is.
it is, right?
Yep.
Cool. Okay. What happens if I repeated the Y twice? So I go A, BC, I do another BC, and then I do BA. So I got A, BC,
Yeah, that
another
works.
BC, and then I do BA. Yeah, that works too, right?
Mm-hmm.
Okay. So here's example one. My X was A, my Y was B, my Z was BA, right?
Yep.
That's what we did. All right, we're going to do another example. Here's my string AAABA. So if I take AAABA, I say starts at 1, sees an A, goes to 2, sees another A, stays at 2, sees another A, stays at 2, sees a B, goes to 3, sees an A, goes to 4.
Yep.
Yeah? Okay.
Yep.
So what's the first repeat visit,
2.
right?
Yep.
Draw a line between that. Got my X, my Y, and my Z. Yeah?
Yeah.
If I get rid of the Y part, so I only have 2 A's and then a BA, is it still in the language?
Yeah.
Yep. What if I double the Y part? A, B, A.
Yeah. So
It
that.
is. All right, there's example 2. I'm just going to do a bunch of these, okay, just to make sure you
Okay.
understand the pattern here.
All
Okay,
right.
here's another one. B, 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 A, B, C, B, A. Trust me, it's accepted. Here's the, oh, I put in the first repeat, but you would have guessed it, or you wouldn't have guessed it. You would have understood, right, that 1 is
Yeah.
the first repeat with this.
1. Yep.
Yep. So I draw the lines. Now X is empty, so we're going to call it lambda.
All right.
Y has a B and Z has all this junk, right?
Yeah.
And it turns out if I get rid of the Y part, this B, B, A, B, C, B, A is B, B, A, B, C, B, A, still accepted.
Okay.
Okay. And if I double the Y part, then I got, what have I got? If I double the Y part, I have 4 B's in a row, right? So I got 1, 2, 3, 4, A, B, C, B, A, also accepted.
All right.
Yeah. So this
Yep.
is what I'm calling my party trick. That if you pick a string that's accepted, you can split it into X, Y, and Z, and you can get rid of the Y part, it's still accepted. You could put in as many copies of the Y part as you want, it still gets accepted. So I'm saying you go to a party, you want to say, hey, we're talking about DFAs. I have a cool fact. Show me a DFA and pick a string that's at least that many letters in your string. Then I can show you how it's accepted.
Okay.
All right, so that's sort of that's the game we're playing. Let's do it again. Here's another bigger string. There's my string. There's my visits. What's the first repeat here?
Uh, 2.
Yep. I draw the lines. I've got my X, Y, Z part. Trust me, if I get rid of the Y part, actually, you don't even have to trust me because if you look at how this works, right?
Yeah.
Um, the first repeat is sort of like here I have A, right? So I'm at state 2. And when I see a BC, it's sort of bringing me back to state 2, right?
Yep.
So, and that is because, can you see my mouse on here as I'm waving it
Yeah, I
around?
can see
Oh,
it.
good. So I mean, and that makes sense because that's what we said. We said the first repeat is where you sort of stop there, you're there, and then you do something and you get back there, right?
Mm-hmm.
So it makes sense that if I put another BC in here, I'd be at state 2. And this stuff is all what I do after I from state 2.
Okay.
Yeah.
Yeah, that makes sense.
Right. And it
Yep.
also makes sense that if I got rid of the BC part, well, I go from state 1 to state 2. Forget about that stuff. I'm already at 2. I can just keep going
Okay.
for real because this is sort of
Yeah. Yeah. No, I
right.
understand.
so I can so I mean, because I'm at state two and I'm um moving a little bit, but I get back to state two, it's like, I walk from I don't know, Robinson to James, and then I wander all over campus, but I end up back at James, and then I go to um Bunce. All right.
All right.
So walk from Robinson to James, go, let's say my wandering is I go to the engineering hall, and then I go to the new engineering building, and then I go back to James. So I got Robinson, James, two engineering buildings, James, and then I keep going until I get to Bunce, right?
Yep.
So the visiting two, and if I just want to get from Robinson to Bunce, I could get rid of my detour to engineering one and engineering two, right? Or Rowan Hall and the engineering, right? And
Hmm.
just say, I'm going to start at Robinson, forget about the detour. I'm going James, do some stuff, James. I'm just going to go from Robinson to James to Bunce.
Okay.
Yeah.
Yeah.
Now, admittedly, that's a bad route, and I should have picked something on the other side of campus, but whatever. But I could also, if I felt like it, I could start at Robinson, go to James, do some stuff, end up at James, do the stuff again, end up at James, do the stuff as many times as I want, end up at James, and then take the James to Bunce route. Does that make
Okay.
sense?
Yeah.
For real, for real.
Yeah. No, I get it.
Okay, cool. Because you are now my model student as to whether people watching this video are going to get it. So I really
All
appreciate it.
right. Yeah.
Okay, so here's another thing. All right, that was just a summary of what we did. We said we split it into X, Y, and Z. Here's what the X was, here's what the Y was, here's what the Z is. Okay.
Mm,
And so here's another, this is the last example. I've got this string. Here's the visits. So what's the first repeat?
4.
Yeah. So this is interesting because the first repeat's at the end. So notice that the Z part turns out to be lambda here because there's no letters under the Z,
Yeah.
right? But we can still do the same thing, right? Because we just do the ABA, right? We
Yeah.
do the ABA. And then look at this, as long as we do an AC, 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 as many ACs as we want, we're back at 4.
Okay.
Yeah.
Yeah.
Which is an except, oops, where'd my mouse go? Which is an except state, so we're okay. All right. So here's my summary of all the different examples we did. Okay.
Mm,
And the interesting thing here is we managed to get a lambda in the X, right? So it's possible that X might be empty. It's possible that Z might be empty. But if you think about the way we did this, let me find the one that shows it the most clearly. Here we go. If you think, well, that's one of them. Do I have another one? Yeah, okay. If you think about the way we did the slices, okay, the Y part can never be empty because here is the closest the lines can be, right?
yeah.
And even when they're right next to each other, when the lines are next to each other, there's still a Y part, right?
Okay.
So we said, you know what? The first line could be right before the Y part, right? The first line you could have nothing before it, right?
Yeah.
That's possible. And the last line, you could have a situation where there's nothing after it, right?
Yeah.
But because of the way I made the game, I said you got to draw a line through the repeats. It's the repeat state that you visit, which means that there's some letter in between.
Okay.
Okay. So, the question is, if you have let's see, is there's a question. All right. So we said, can X equal lambda? Sure. We saw an example. Can the Z part be equal to lambda? Absolutely. We saw an example. But can the Y part be equal to lambda? No, because we do this because of the way we slice it, right? And we say pick two states that are repeated. There's always a letter in between them, at least one.
Okay.
For real?
Yeah.
Okay, cool. So is XZ in your language? Yeah. Is X with a bunch of Y's in language? Yeah, because whatever your repeat is, you're saying, do something, then you end up at state 2, do something else. Where'd my mouse go? Come on back. You end up at state 2. You do this Y part, which is like a detour that takes you back to state 2. You can do that detour as many times as you want and end up at state 2, right?
Yeah.
And then you keep going from there, wherever you were going in the first place, right? So you could have 517 copies of Y, and that string would still get accepted.
Okay.
Yeah, so I could have 517 copies of BC. So I could do A, BC, 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 and I could do that BC 517 times, and then BA, it'd still be accepted.
Okay.
Okay, yeah, makes sense?
Yeah, no, I get that.
Okay, cool. All right. So if we always use this weird method, then yeah, all these strings are in my language, right? Basically,
Mm.
so this is what I'm saying is a party trick now, because you can say, ooh, you know what? Give me a string in the language and tell me, you don't even have to show me the DFA if you tell me what the first repeat is, so I can split the X, Y, and Z. And then I can give you as many more strings as you want that are going to be accepted just by doing this split,
Yeah.
right?
Okay.
So, you can hide the DFA from me so I don't even see it anymore. But if I know this picture, right, if I figured out my split, I can give you 500 more strings if you want, right?
Yeah.
Okay. All right. The next question is, what's the furthest apart? This says, what's the maximum length of the concatenated string XY, which is basically saying, what's the farthest apart that these two splits can be, right?
Yeah.
So if I have 5 states, do I draw a picture of it? Yeah, this is a crappy picture. But anyway, suppose if I have 5 states, right?
Yes.
If I have a string with 5 letters and I visit 6 states, then I'm going to have a repeat because there's only 5 states, right? So one of
Mhm.
these guys is a repeat.
Okay.
Does that make sense?
Yeah.
I just put in wacky Greek letters to show you because I didn't want to say what I visited,
Yeah.
right?
Yep.
But, let's suppose that I made my first cut right here at the very beginning, right?
Like before the
Well, if this alpha, so these are my letters here. That's my string. So my
A.
string
Yeah.
is like A, B, C, B, A or something, whatever, right?
Okay.
Well, actually, we can see it. If I make, we had an example. Uh,
That was where it was lambda in the front.
yeah, it was where it was lambda in the front and, oh, did I not give you one that's lambda in the front and lambda in the
Yeah.
back? I wonder if I can do that.
No,
Yeah.
I think you did.
Now I didn't in these examples, but that would have been good. So if I think about it, I could do, yeah, no, the way I made this, it can't be lambda in the front and lambda in the back.
Oh, at
But
the same time.
you
Like,
could have it. Imagine that I sliced right here
yeah.
and I sliced right here, right?
Yep.
If I slice on the first one and I got 1, 2, 3, 4, 5 different things here, this is the last place I could slice, right?
Yeah.
Because there's only 5 states and there has to be a repeat by the time I get to 6 by the pigeonhole principle, right?
Okay.
Yeah.
Yeah.
So, um, so if I have 5 states, the XY part, if I slice at the beginning and the end, the longest the XY part can be, I can't write on these slides, can I? Is there a way to like edit slides full screen and show? Blah, 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 blah. No, it's not going to let me do it. But basically, what I'm trying to say here is if I have 5 states and I have a string with 5 letters, the X could be lambda and the Z could be lambda, or sorry, actually, let's try again. If I have 5 states and I have 5 letters, the biggest the XY could be, right?
Yeah.
The best I can do for my second circle is this very last guy, right?
Mm-hmm.
Which means that if I squish the X and Y together, the second cut is the end of Y, right?
Okay.
So if the second cut is the end of y, and this could be my second cut when I have 5 letters, that means if I have 5 states and a string with 5 letters, when I squish the XY part together, I concatenate them, it could be all 5 letters
All
are
right.
the XY part. Yeah.
Okay.
I had 5 letters here, right?
Okay.
And the first time I saw the repeat was my sort of sixth step, right? Because I could do 1, 2, 3, 4, 5. Those could all be different. But after I've done 1, 2, 3, 4, 5, because I forced it to be 5 letters, I have to take one more step, right? 5 letters, 6 states.
Yeah.
And now I've only got 5 states. So something's got to repeat, right?
Okay.
Yeah.
Yeah.
So the biggest that the XY part can be is all the letters.
Okay.
For real?
Yeah, now I get that.
Okay. Um, so, and even if I had, 20 letters on here, the biggest it could be is 5 letters because there's only 5 states. So after I get to state 5, I got to do a repeat.
All right.
Yeah.
Yeah.
So if I have 5 letters, right, the biggest the XY part can be is 5 letters long.
Okay.
Yeah.
Yeah.
Okay, cool. Say, you were going to say something?
No. No.
Okay, because of the way I do these repeats, right?
All right.
Okay. So the point here was so this stuff was our party trick. This was me just saying, look, I could go to a party and I could say, hey, if you give me a DFA with 5 states and you give me a string with at least 5 letters, I can mess with it and show you lots more strings.
All right.
Okay.
Yeah.
And because you give me a string with 5 letters, I know your DFA has to be infinite because there's only 5 states. So 5 letters means six, start and then 5 more jumps, which means you have to have a repeat. Okay. So what I've got here is if you have a DFA with M states and you have a string with M letters, the XY part, right? You only have M states. If you have M letters, then you have to have the start plus M more states that you visit, right?
Okay.
Which means that's M plus 1 states, but you only have M states to visit. You got to have a repeat,
Uh,
right?
yeah.
And so the biggest that the XY part could be under those circumstances is M, it turns out. Okay. Just
Uh,
like when we had 5 with 5 letters, the biggest length of the XY part could be all 5 letters. If you have M letters and M states, the biggest it could be is M letters.
all
Right.
right.
So, and the question is, could the length of X plus the length of Y be longer than M? And the answer is no. So this is the sort of important thing that you want to remember for the next lecture is length of X plus length of Y is always less than or equal to M.
Okay.
And sometimes we say that as the length of the XY part is less than or equal to M,
All right.
right? Because the XY part is just squishing them together. All right. Assume our DFA has M states and accepts the language L. And you pick a string that's accepted by our DFA and has at least M characters, right? So instead of 5 and 5, I'm doing M and M, but same thing.
Okay.
Yeah. We know the string equals this XYZ, right? Because that's what I
Yeah.
did. I split it up into XYZ.
Yeah.
Yeah. We know that because I told you you had to have at least M letters in your whole string, the length of the string is greater than or equal to M, right?
Okay.
Because I told you so. And that
Yeah.
means the length of the X part plus the Y part plus the Z part is greater than or equal to M.
Okay.
Because that's just what the string is it's the X, Y. So we know the length of the X, Y, and Z part is greater or equal to M. That means the length of your string is at least M letters.
All right.
We know that the XY part, when you just squish that, it can only be M letters at maximum.
Okay.
All right. So The whole point of all of this, we're up to slide 72, all the stuff before this, 2 points. And I'm glad that I'm recording this because you can look at it again to get the 2 points, and other people can now look at it to get the 2 points. So again, thank you for letting me.
Yeah.
But the two big points, all right. Point one, there's this funky thing where you split it into the X, Y, and Z, and it gives you a chance to make a whole bunch of other strings out of it, right? That's what I called the party trick. Okay.
Yep.
Part two, you don't have to exactly remember how did we come up with this. The length of the X and the Y and the Z part has to be greater than M. That's just the string is at least M characters long. And how we came up with this X and Y part is less than or equal to M. That's just sort of, these are going to be facts that I give you. And we also said we know that the Y part isn't empty, right? Because of the way
Yeah.
we draw the lines. Now we can do something really cool. And the cool thing is that somebody proved that you can do this with any regular language. Okay, you can do this XYZ thing. All right.
Yeah.
They proved that. So that means that if I want to prove that a language is not regular, right? Because that's sort of the big picture we're trying to get to. There's some languages that aren't regular. Then I can do it using a proof by contradiction. I'm going to say, let me assume the language you give me is regular. And if I assume it's regular, then I can find a string. If I assume it's regular, that means there's a DFA for it, right? Because we said all regular languages have DFAs.
Okay.
And if there's a DFA for it, since a DFA has a finite number of states, I'll call the number of states M. I'll pick a string that's too long, and then I'll show that I'll pick a string that's at least M letters long, so that the people told me I should be able to do this Y repeat thing. But I'm going to show you can't do the Y repeat thing. So there's a contradiction. It must not be regular. This is sort of the heads up for the next lecture. I'll explain it a little bit more in there. Before we did pigeonhole principle, we'll skip
Okay.
that. So this thing is called the pumping lemma. And a lemma you can think of as just like a smaller theorem, right? A theorem that might help you prove something else. And what have I got here? Theorem. This is all from the next set of slides. I might have actually okay, yeah. So there's a statement that says if a DFA recognizes an infinite language, it must have a loop in it. Okay.
Yeah.
And here's my argument. And I used to do this argument without the party trick, but now that you've seen the party trick, probably it'll make more sense. Suppose D is some DFA that recognizes an infinite language L, right?
Yeah.
There's some number M, which is the number of states. Maybe it's 5, maybe it's 25, but the DFA has to have some number of states, right?
Okay.
Since my language is infinite, I can always find a string in my language that if I pick some number n, suppose I say 53, I can always find a string that's more than 53 letters long because it's an infinite. So there's got to be, something in there, right?
Okay.
Infinite languages have to have strings that keep getting bigger and bigger. So if I pick a string that has the number of letters in the state, as a number of letters is the same as the states, that string has to visit m plus 1 states, right? Because you got to start and then do m steps, which gives us m plus 1 visits.
Okay.
But you only have m states, so somebody gets visited twice. And so that means there's a loop in the DFA. And this is basically saying what we saw with the party trick. If you have a DFA with 5 states and you visit 6 states in your journey, somebody's got to get repeated. The only way you can ever repeat is if you have a loop. Make sense?
Yeah, that makes sense.
All right. So blah blah blah. Um, and this again, these are slides from before I made the whole party trick, but suppose you have a DFA called D, then here's one example of a DFA. This is just some random DFA I made up, okay? To try
Yeah.
and give you a specific art example, right? Suppose D recognizes a language L. Well, this recognizes the language, let's see, has to start with an A, B, and then it can have as many either as many, you can take this thing to get used with an A or B and then go back with the B. So you could have A, B, A, B, 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 A, B, A, B, whatever, right?
Okay.
All right. So I've got a DFA and I have a language that accepts. M is the number of states in the DFA. So in this case, M is 4, right?
Yep.
S is a string that has at least M letters in it. So I picked the string A, B, 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 right? 4 letters, 4 states. Since S has M letters in it, it visits M plus 1 states. It starts and then it does A, B, B, B. So there was the start state plus the one after each of those letters. So it visits 5 states, right?
Yep. Okay.
But S visits M plus 1 states. D has M states. So one of the states has to be a duplicate. In this case, my M is 4. And look at that. 3 got doubled and 4 got doubled, right? I had 2 duplicates, but I just
Yeah.
cared that there's at least one, right? And this was from me saying, okay, that's one example, but it works for any general example too. Yeah.
Yeah. Would it work if you drew a line between like the second state that got visited twice? Like if
Yeah, in fact, it would work. So you're absolutely right that the party trick would work every single time. Even if you put it there, because again, you get to somewhere and you do something and you get back there. So party trick would work wherever you draw the lines. We draw the lines at the beginning so that I can get so that I can say, here we go. So I can say this thing, right? The X and the Y part have to be less than or equal to M.
okay.
Right? If you draw the line somewhere else, the X and Y, the number of letters in the X and Y part combined might be more than that.
All right.
All right. So the way I did the party trick was so that you could have this thing, but you're absolutely right that if you're at a party and you want to pick a different, you could say, well, here's a 2 and here's another repeat of a 2 over here and draw the lines there. And that
Yeah.
means you could repeat this whole piece because it's a path from 2 back to 2, right? So you
Yeah.
can repeat as many times as you want, and that'd be fine. Yeah.
Yep.
Okay. So let me pull up the other slides now because the next lecture will make more sense having seen this one.
All
Yeah.
right.
So I'm going to tell you that that there is another full lecture for this slide set that's probably pretty close to what I'm going to do now, apart from the very beginning of it.
Okay.
And so you might want to watch that too,
Yeah, I
having
would.
seen this stuff. But and I'm not going to take it down when I put this one in. Can you go a little bit past 10?
Yeah. Yeah. That's fine.
Okay, cool. So yeah, I mean it is now worth. I shouldn't go far past 10, but on the other hand, um, it is useful to get this in as a video, so why not just do it?
Okay.
Okay, so but it's fine. All right, so um uh previous lecture, pumping letter background, thinking about DFAs and strings they accept and what happens when you have an infinite language. That's what we just did. This lecture, I want to teach you what people mean by when they say I'm going to pump a string. I'm going to show you the pumping lemma, and then I'm going to do a bunch of proofs that use the pumping lemma. Okay. So the first few slides here are just reminding us what we did in the previous set of slides, right? So we could, X, Y, Y, Z is in the language, and X, Y, Y, Z is in the language. And, if our DFA had 54 states Any string in language that was at least 54 characters long, we'd have to visit a duplicate, right? So X, Y, Y, Z would be in there, and X, Z, so I could get rid of the Y, or I could put 3 of them in, or 2 of them in, or 4 of them in, or whatever. Yeah?
Yep.
All right. Our DFA had M states. Any string in the language that's at least M characters long has to visit at least one state twice. So I could double the Y or get rid of the Y or put 3 Ys or 4 Ys, whatever. All right. So let me tell you what I mean when I say I want to pump some string in a language. So start out by saying pick a string in the language and make sure that the size of the string, the number of letters in the string, is at least M characters long. And I'm going to tell you M's the number of states in the DFA, but I'm going to pretend like sort of we don't necessarily know what M is eventually, right? I'm going to say, oh, you can't see the DFA, but somebody told you that there's at least M letters in it, and they told you it's 25, or they told you it's 30, or they told you it's 45. Yeah.
Yeah.
You got to pick a string that's at least that's in the language at least. All right. So you split the S into 3 parts. And when you see this in the textbook, it'll just say, oh, you split it into 3 parts, X, Y, Z, such that the length of X, Y is less than or equal to M, right?
Yeah.
And the length of Y is greater than 0. And the textbook doesn't necessarily show you the whole, oh, look, we figured this out because of the party trick. But we know because of the party trick that these are what we got, right? When we figured it
Okay.
out. Okay. But you don't really need to know the party trick to do any of this. I just think when I threw these things at people before and just said, look, split your string so that the string is XYZ and you got the XY part and the length is less than or equal to M and the Y part is bigger than 0. People were like, I don't understand. What do you mean an XYZ part? What do you mean? How come? How come? How come?
Yeah.
So the whole party trick is to give you some idea of how come. Okay.
Hmm.
And what I'm going to do is I'm going to make up this function that I call pump. And when you pump S, which is my string, the second parameter to my function is how many Y's you put in it.
Oh,
So pump S of 0, 0 Y's. Pump S of 1 has 1 Y, but when you have S of 1, that's the same as your original string, right?
yeah.
Pump S of 2 has 2 Y's, pump S of 3 has 3 Y's, and so on, right?
Yep.
Where this is just, copy the repeated letters as many times as you need to. Yeah?
Okay.
All right. So lots of computer scientists talk about pumping a string. This pump function that takes 2 parameters, that's mine. So, if you talk to people about the pumping lemma, they won't know what you mean when you talk about this function, but
All
they'll
right.
know what you mean when you talk about pumping a string. They know
Okay.
that it means putting in more Y's or getting rid of Y. They just haven't seen it quite laid out like this. Okay.
Yep.
So now I'm going to take a language, and this is the language A star B star, which is the language that has 0 or more A's, but as many A's as you want, and then 0 or more B's, as many B's as you want. But all the A's have to come before all the B's. Okay. All right. So I'm going to talk about this language, but this is really a regular expression. So really what I should say is, here's my language. Oh, crud. This is my language because a language is a set of strings, right?
Okay.
But since this is an easier way now that we understand regular expressions to draw this, I figured I would do it this way and not like that. All right.
Yep.
Okay, fine. So I want to pick a string. I want to pick a string in this language where the string's in the language, so it's got a bunch of A's and then a bunch of B's. And the length of the string is at least M characters long, where M is the number of states in the DFA. But I'm not going to show you the DFA, okay?
All right.
I'm trying to make it hard by not showing you the DFA. And so I'm going to say, what could I do so that I know that I have that many letters? And what I'm going to say is, look, if I just treat M as a variable, I could say, well, if I have, pretend M was 5, then I'd have 5 A's in a row, or 5 A's and then 5 B's, or 5 B's, or 2 times 5, so 10 A's, or 5 A's and 10 B's or 25 B's. All of these, if I said M was 5, those would all be at least 5 letters long. If I say M is 500, well, then I got 500 A's and 500 A's and then 500 B's. You with me?
Yeah.
So no matter what M is now, I'm like being really clever here and saying, you know what? I don't really care what M is. I'll just write M. Yeah.
Yep.
So you can tell me later what M is. If you drew out the DFA for this, you could show me what M is. But right now, it doesn't matter to me. I'm just going to use M as a variable. And if you tell me M is 5 and then you say, oops, I messed up, M is 7, right? There's 7 states in my DFA. I don't care because I just said, oh, well, pick A to the M is my string.
Okay.
For real?
Yeah.
Okay, cool. So I'm going to pick a string in here, right? So what I want to do is I want to pump this thing, right? So I need to pick a string that's in the language and the length of the string is at least M letters long. Well, do you agree that each of these strings is in the language of some A's or 0 or more A's followed by 0 or more B's?
Yeah.
And do you agree that all these things have at least M letters?
Yep.
All right, cool. So I gotta pick a string that's greater than or equal to M. Yeah, note that all these are in language and they're at least M letters long. I'm going to try pumping this string, A to the M. It's in my language. I just want to show you how I do it. Okay.
Okay.
All right. So, um, my language is A star B star, and the first example I'm showing you is my string is A to the M. Okay.
Yep.
Right. That's what we picked. All right. Well, A to the M is this, right? It's a whole bunch of A's. If M is 5, it's only 5 A's. If M is 30, it's 30 A's. I don't know exactly how much it is, so I'll just say it's M A's long. Yeah.
Yeah.
Okay. And I had to make sure that um, my string was in the language. Well, it is. And my string's at least M letters long. It's exactly M letters long, but that's greater than or equal to M, so I'm good. Okay.
Okay.
All right. So I want to do the split into X, Y, and Z. Okay. Which
Yeah.
you'd think would be pretty hard because we don't know what it is yet, but actually you can do the trick. So what you do is you say, all right, whenever you split into X, Y, Z, you pick the Y first. Okay.
Yeah.
Now, when I say, oops, when I say, what does Y look like? Go away. What's this thing here? When I say, what does Y look like? Well, tell me what letters are in Y.
A.
Yeah, exactly. There could be one A. We don't know. Y could be all MAs, right?
Yeah.
Um, see, but we know Y's got to be bigger than 0, and we know the XY part has to be M letters at most, right?
Mm-hmm.
You're absolutely right. Y is A to the something, but I don't know what it is, right? So I'm just going to say A to the K. I like using variables. What the heck, all right?
Yeah.
So Y is some number of A's in a row. How many A's in a row? K of them. And what could K be? Well, K has to be greater than 0 because we said Y can't be empty. And it could be that Y takes up all the letters in the string. So K could equal M, but Y could only also be just a part of this. Does that make sense?
Yeah.
All right. So formally, when I write this, I say Y is A to the K, where K is greater than 0, Y has to be at least one of them, and it could be as many as you want. All right. So
Okay.
now I've picked my, well, I say I've picked my Y, but I've said what Y is, right?
Yeah.
And after you say what Y is, you have to say what X is. All right. Well, what's X? What's the smallest X could be? Well, it could be lambda, right? Because we said X could be
Yeah.
lambda in this trick. Yeah.
Yep.
If it's not lambda, what letters are in X?
A.
Yeah, it's going to be A's, right? So I said, how many A's? Well, I'm going to make another variable up. It's got PA's, all right? But if I imagine that the A's are jelly beans for a minute, okay? If I have, let's pretend I have 75 jelly beans, yeah?
Yeah.
And the Y already took 25 of those jelly beans away, then there's only 50 jelly beans left for the X to use up. Make
Okay.
sense?
Yeah.
So instead of saying P is greater or equal to 0 and less than or equal to M, I can say, well, since I already used up K of the A's here, P has to be less than or equal to M minus K, right? So like 75 minus 25.
Okay.
All right. So X can have all of the rest or none of the rest or something in between. Again, our problem is in the examples that I gave you in the previous slide set, you knew exactly what the number of states were and how you split it and what's the duplicate. And now I'm like, haha, I'm not showing you any of that.
Yeah.
And what can you do if you don't know that? Well, we could do a lot if we have an easy string like this, right?
Yeah.
I picked all A's on purpose. Yeah.
Yep.
And then you say, what's Z look like? Well, suppose X or Y took 25 out of 75 and and X took, so we had 25 out of 75 and then X took 10, right?
Yeah.
So we had 50 for X to choose from. It took 10. So now there's only 40 left. Well, Z gets all those, right? Because the string is XYZ.
Okay.
Yeah. Does that make
Yeah.
sense?
Yep.
Right? Because remember, we're splitting it. So like this is the X, and then that's the Y, and then that's the Z. So what Z is all of them, all is just A's. How many A's? You start with M, but then you take away P and you take away K because you're taking away the A's that these guys already used up.
Okay.
For real, okay?
Yeah. Yeah. No,
I
I
mean,
understand.
and this is something the class had a lot of trouble with too, and that's where I came up with this jelly beans thing, right?
Yeah.
Y gets, if we make it just down to if there's only 10 letters here, and Y takes three of them, then the X part could only have as most seven, right? If there's 10. So, and suppose the Y takes three from the middle or something, right? Or maybe it takes these three. Um, and if the X takes two, well, the Z, because the string is XYZ, the Z has to finish it off and do all others. Okay.
Yeah.
All right. So we did this and we said Y is A to the K with some restrictions, and X is A to the P with some restrictions, and Z is A to the everything else, right?
Yeah.
And now I want to do the pump, right? And remember, the pump function just says take zero Y's or take one Y or take two Y's or something, right?
Mm-hmm.
And so what I'm going to do is say, what's XZ? Well, I can just write this out. XZ equals copy the X and copy the Z. So I got A to the P, A to the M minus P minus K.
Okay.
I just copied these two. So far, so good?
Yeah.
Okay. Now here's the tricky part. What I'm doing here is this says I've got PAs in a row. Yeah?
Yeah.
Okay. And then I squish onto that M more, but then I take away P of them, and then I take away K. So basically, how many A's do I have? Well, I have P plus M minus P minus K. Well, the P's cancel out. Yeah?
Okay.
So I end up with A to the M minus K. Yeah?
Yeah.
So for real, yeah?
Yeah. No, I get it.
Okay. I know it's early, and also we've just done an entire lecture at lightning speed. Now I'm in the
Yeah.
next, but recording this is good because then you can go back and watch it as soon as
Yeah.
I post it. I will post it soonish. Um, I might even put it on the Canvas so people can see it there too, as well as on YouTube. Because it'll be useful for my YouTube so that people in future classes can see it, but also Canvas is useful. So, all right. Anyway, so what I have here is I just did the math. I said, here's what X is, replace it. Here's what Z is, replace it. And then I said that equals A to the M minus K. And notice that my language was A star, right? Or sorry, A star, B star, right? As many A's and as many B's as you want. And so a bunch of A's is still in A star, B star, right?
Yeah.
Still in the language. If I pump S1, well, that's X, Y, Z, right?
Yep.
We better make sure that when I write X and then Y and then Z and then do the math, it works. So X, I copied X. X is A to the P. Y, I copied Y. Y is A to the K. Z, I copied Z. That's A to the M minus P minus K. So do you see how I got this piece?
Yeah.
I just copied the X, Y, and Z. And then I said, all right, this is a whole bunch of A's in a row. How many A's in a row is it? Well, P plus K plus M minus P minus K. So the K and the P, those guys cancel out. I end up with A to the M, right?
Yeah.
And I say, look, pump of S1, A to the M is in A star, B star. But I also say, oh, yeah, A to the M, that was my string that I started with. And I say, thank goodness that's the string I started with because that's what XYZ should be.
Okay.
All right. If I do X, Y, Y, Z again, I just plugged in what's X, what's Y, but I put 2 copies of it this time, right?
Yeah.
What's the Z part? I shouldn't have that there yet. So X, Y, Y, Z is this thing. When I simplify it, I have to add P plus K plus M minus P minus K. Well, I end up with M plus K because one of the K's goes away and the P goes away, but not both of them. Does that make sense?
Yeah.
And it's still A to the M plus K, right? So it's still a bunch of A's that's in my language, right? And
Okay.
same thing when I do X, Y, Y, Z, I put the X, which is the A to the P, I put 3 copies of the Y, I got the Z, right?
All right.
And I simplify it and we're good. Yep.
Okay. Yep.
Okay. Now I picked this A to the M string. I could also try and do it on this A to the M, B to the M string because theoretically, no matter what language I pick, there's a way to, as long as it's a regular language and it's an infinite regular language, which A star B star is, then I can I can pump it, right? So my language is still A star B star, but I'm picking a different string now. Now I'm picking M A's in a row and then M B's in a row. Okay.
Yep.
All right. So here's what it looks like. Does that make sense? Bunch of A's and a bunch of B's.
Yeah, I got it.
And again, I don't know what the DFA looks like. I don't know if M is 5 or 75. I just know that it's M. That's okay. I don't need to know. Yeah.
Okay.
So I'm going to do this split again. I have to split it into an XYZ. And this is where some cool stuff happens. The, the XYZ that I'm splitting it into, the XY part, it says is less than or equal to M letters long, right?
Yeah.
That means the XY part has to come in the first M letters. Okay.
Okay.
If the XY part comes in the first M letters, then the X part and the Y part come in the first M letters, right?
Yeah.
What's Y look like? What could Y be?
Just like A. A.
Yeah, Y is a bunch of A's again. Same thing as we had again, right?
Yeah.
Does that make sense? Because Y has to, because of these cool rules that we made, and this is why picking that first repeat is important,
Mm-hmm.
means that I can say, yeah, I've got the string A to the M, B to the M. But when I'm trying to figure out what X and Y are, they're just the stuff in the front. Yeah.
Okay. Yeah, I get it.
So Y is still A to the K. What's X? Well, X is A to the P. I mean, P is a variable name, K is a variable name, but I just did it the same because it's exactly the same math, right?
Yeah.
Where P could be 0, could be bigger, can't be more than the leftover M minus K A's, right? X has to come before the Y. Now, the Z part's a little harder. The Z part is any of the A's that got left over, like before, and then all of the B's, because we didn't use up any of the B's yet, right? And
Yeah.
the XYZ has to be my whole string. So Z is, well, this is what we had before, A to the M minus P minus K, and then M B's in a row, because all the B's we know are part of Z. Good?
Okay.
For real.
Yeah, I got it.
Okay, cool. So I got my XYZ. I can do the same pump thing again, right? And I can say, what happens if I get rid of the Y? Well, I end up with this thing. I do the math. It's this, and that's in the language. I can pump it with 1. It's XYZ. Well, that should be my original string. It is. Let's just look at, did I do an S3 on here? Yeah, let's look at S3, okay? It's X, 3 Ys and a Z. Well, what's the X part? The X part is A to the P. The Y part is A to the K, so I repeat that 3 times. The Z part, I just copied this whole thing. A to the M minus P minus K, B to the M. Yeah?
Yep.
And then I said, all right, let me do the A's. How many A's do I have? I have P plus 3K plus M minus 1P minus 1K, and then all those B's, which means it's A to the M plus 2K, B to the M. Yeah, because I had P, but I took away P, and I had K, but I took away K. But I still had the K and this K and the M. So my math just ends up like that,
Okay.
right? And then all the B's, right?
Yep.
But pump S3 should be in my language by the pumping lemma. The pumping lemma says it is. And if I look at this, sure, it's a bunch of A's and then a bunch of B's. Yeah?
Okay.
All right. So the tricky part with these problems, and right now I'm just showing you how it works with regular languages. In a minute, I'm going to show you how it works if the language isn't regular. This trick that we did, you can do this pumping trick for any infinite regular language. You got a regular language that's infinite, it always works for whatever string you pick, as long as the string is in the language and is at least M characters long. And we just showed that even though we don't know what M is, right? I mean, where M is the number of states in the DFA, even though we don't see the DFA, we can't figure out what M really is. We could just do it as a function M and it works. Yeah.
Yep.
But you can't always do it when the language is not regular, right? So sometimes it works when language isn't regular, but not always. And so the magic of it not working sometimes is if you've got an infinite regular language. Oh, so this is what the pumping lemma says. And we're going to use this for doing our proofs that a language is not regular, but this doesn't say anything about not regular languages. The pumping lemma says informally, if you've got an infinite regular language, then there's a DFA for that language. Pretend you know how many states are in that DFA. We always call that number M. Any string in the language that's at least M characters long can be pumped using that thing that I showed you before, right? So that we can make more strings in the language, right? So that's the sort of unofficial definition of the pumping lemma, right? And again, doesn't say anything about proving that languages are not real. It just says proving stuff is real, right?
Yeah.
Sorry, is regular, not regular. Okay. All right. Now, if you look on Canvas, the first is my outline of how you want to prove, how you can use proof by contradiction. You probably saw proof by contradiction in discrete, but I'm just going to remind you of how it works.
Okay.
Okay.
I think I have that. Did you give
Yeah, I
that?
think you probably do. I think I probably handed this out. This is but this is yes, I found it on Canvas. I was just missing it amongst all the other stuff that was on Canvas.
All
But
right.
yeah, this is in Canvas. So did I do the cupcake example with your class?
I think so.
Yeah, I'll do it again for the video anyway. So here's my sample of proof by contradiction. There was a story I heard about a birthday party for 3-year-olds or something, where everybody got cupcakes and the parents are in the kitchen and the kids are in the
Yeah, I
living
remember
room or
that.
something. Yeah. Um, uh, yeah, sure. Let me give you this anyway in the middle of the video so people have it. And one kid comes in with icing on his face and says, well, I didn't get a cupcake. And the parents are like, you know, Well, I don't know how the parents reacted. I don't know what the right reaction is, but let's suppose for a minute that the parent wanted to prove to the child that they knew without any, they knew for sure that the child had had a cupcake. All right. Statement, I want to prove the child ate a cupcake. Assume the statement is false. That is, the child did not eat a cupcake. All right. And then you do some clever stuff, like you say, okay, if the child did not eat a cupcake, then there is no way the child could have come in contact with icing. And if the child does not come in contact with icing, then there's no possibility there could be icing on the child's face. But wait a minute, there's icing on the child's face, but there can't be, but there is, but there can't be. So I have this contradiction and I draw this symbol that looks sort of maybe like four arrowheads hitting each other. It's a contradiction. Thus, my assumption must not be true. What was my assumption? My assumption was the kid did not have a cupcake. Thus, we have proven by contradiction that the kid did have a cupcake, right? That the statement that was up here is true. Okay, that's the outline of a proof by contradiction. Right. We've also got a what I call a pumping lemma proof. Okay, it's really a pumping lemma proof is that a language is not regular. Okay, and here's what we're going to do. We're going to do the same sort of outline, except instead of trying to prove that the kid ate the cupcake, we're going to try and prove that some language is not a regular language, right?
Okay.
And so we say, let L equal the language. Let's assume that the statement is false, right? What was
Yeah.
my statement? L is not a regular language. So what is the statement false? L is a regular language, right?
Yeah.
Then it follows that, and I say, let M be the number from the pumping lemma. Then I say, let S be, and I pick some clever string, right? Not just any old string, but I pick a smart string, which we'll talk about in a minute. And then I have to pick a string that's in the language, and I have to pick a string that's at least M letters long, just like I did before with A to the M or something, right?
Yeah.
And then I say, the pumping lemma says the Y part can't be lambda, and right, the Y part has to be at least one character long, and the XY length has to be at most M, right? And then I do the math like we did before and say Y has to equal blah, blah, blah. X has to equal blah, blah, blah. Z has to equal blah, 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 right?
Mm-hmm.
And then by the pumping lemma, and I say, oh, sometimes I say X, Y, Y, Z should be in my language, or X, Z should be in my language. And then I do what is X, Y, 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 Z, or I do X, Z, and I say, oh, look at this. It's not in my language. Thus, my assumption must not be true. Thus, I prove my contradiction that this language is not regular, right? So that's sort of the outline. So now let's look at it in the slides, right? Okay. Dr. K's sort of hand wavy version of pumping lemma. If you've got an infinite regular language, there's a DFA for that language. Pretend you know the number of states. We always call it M. You can pump any string, right? That's what I say the pumping lemma says. And so the hack is if you can find just one string in the language that can't be pumped, then the pumping lemma tells us the language isn't regular. And so the way the hack works is this is sort of like the outline, the proof by contradiction outline we had before. Assume it's regular, pick some string, show that when you pump it, it's not still in the language, and then you've got a contradiction. So this, what I was saying before, this is the formal definition of the pumping lemma. It's messy, but when you read it in the book, you'll be like, oh yeah, that's the same as what I had, right? What Dr. K was hand waving. We've talked about proof by contradiction before. And this says it's an outline, but it's not quite as good as the outline that I showed you, right? My fill in the blanks outline. Okay. So now what I'm going to do is I'm going to prove that A to the N, B to the N, such that N is an element of N, is not regular. And the difference here is that now I have to have the same number of A's and B's. Before, I could have a zero A's even and N B's and 50 B's or whatever. Right now, if I have lambda in the language, that's zero A's and zero B's. I have A B with one of each. I have A B with two of each, right?
Yeah.
Three A's, three B's, 50 A's, 50 B's, whatever. But I don't have like zero A's and 50 B's. I don't have two A's and five B's, right? Those aren't in the language. Okay.
Okay.
So, but the proof is going to look a lot like our previous proof. Let's say that L equals A to the N, B to the N, right? And assume L is regular. And this is going to look very much like that outline. In fact, it's not going to be perfect, but it's going to be pretty close to the outline that I gave you before. Let M be the number from the pumping lemma. We don't know that it's, that we're trying to have M states or whatever. We just say it like this. S is A to the M, B to the M. This is the hardest part. What's a good string for me to pick? And I picked this string just like I picked it before, because I know that means the XY part has to be all A's. Right? Okay. How did I decide to pick this string? Well, I've seen a bunch of examples, so we're just going to go with it for now, right? Since my string is in the language, right, same number of A's and B's, and the length of the string is at least M characters long, because how many letters are there in this string altogether?
Two.
2M, right?
Yeah.
Yeah, 2 times M, exactly. All right, so pumping lemma applies. By the pumping lemma, I could split S into X, Y, Z, where Y isn't empty and the XY length is less than or equal to M. Since the length of XY is less than or equal to M, XY must just be A's, just like we did before, right?
Yeah.
So Y has to be one or more A's. Yep.
Yep.
So I'm going to say, let's suppose Y is A to the K, just like we did before. Pumping lemma says X, Y, Y, Z is in L. So now I'm going to do the math to figure out what X, Y, Y, Z is. And okay, I used Q instead of P here, but it's the same thing, right? When I do X, Y, Y, Z, I find out that X, Y, Y, Z is A to the M plus K, B to the M. Okay, just like we did before.
Okay.
Okay. But here's the thing. X, Y, Y, Z is A to the M plus K, B to the M. Before, when we were doing regular languages, my language was as many A's as you want and then as many B's as you want. So this was okay, right? But now I'm saying, I want the same number of A's and B's. And this for sure isn't the same number of A's and B's, because I've got K more here and K's greater than 0. You with me?
Yeah.
All right, so pretend we pasted the math in here. So X, Y, Y, Z equals this, and K is greater than 0. So X, Y, Y, Z is not in the language, right? Because the language is the same number. Yeah,
Okay.
right? This language
Yeah.
says you got to have the same number of A's and B's. But I
Okay.
have K more A's than B's here, right?
Yeah, because X and Y is all A's.
Yeah, because X, Y, Y, Z is in the language, right?
Yeah.
Right. And so I did the X, Y, Y, Z math just like before, and I said, here's what it equals. Da, da, da. And I said M plus K A's, but only M B's.
Yeah.
All right. So X, Y, Y, Z isn't in my language because I'm supposed to have the same number of A's and B's. But the pumping lemma says it should be in the language, but it's not. But it should be, but it's not. But it should be, but it's not. So that means we have a contradiction. Our assumption must be false. What was our assumption? We assumed, that L was regular, right?
Yeah.
Our assumption is false, so L must not be regular. Yeah?
Yeah. What does QED
Oh,
mean?
QED. QED means I'm done my proof. I think it stands for quod erat demonstrandum in or demonstratum in language,
Okay.
in Latin. And you just write it at the end of the proof to say, haha, I'm done. It's just like a right.
Yeah.
Some people say QED stands for quite easily done, which means but basically it's my proof is done, I'm done, right? No
Yeah.
more, it's done. Yeah, good question. Thank you. Um, And so, yeah, here's the outline that I follow. An infinite regular language, there's DFA. Pretend you know how many states are in that, call it M. Every string in the language that's at least M characters long can be pumped to make more strings in the language. But if we can find just one string that can't be pumped, the language must not be regular, right? So if I say everybody in our class wears glasses, but there's one student who doesn't wear a class, then my everybody statement has to be false, right?
Okay.
Because when I say everything, it's always true. If you find one thing that's not true about it, then you can't say it's always true anymore,
All right.
right? And so that's the trick here is we say, because the pumping lemma says you can do this with every string, if you can find one that can't be pumped, then the pumping lemma, then you're like, can't be regular. Just like I could say, can't say that everybody wears glasses because somebody doesn't.
Okay.
All right. So, right, hard thing about proving language isn't regular is how do you pick a good string to use? You know, starting with M of something is often very good. Okay. Um, it has to be in the language, has to be at least M characters long, but it's not a random choice, right?
Mm-hmm.
Because the first M letters include the MY part. And this is where I said, oh, you know what? I picked all A's, so we could say it was all A's, right?
Yeah.
And this proof would have worked perfectly if I said A to the M times 2, B to the M times 2, because the first M would still, in fact, the first 2M, right? There would be double as many A's at the beginning, would still work.
Okay.
So 2 times MAs and 2 times MBs. So that means that, so Y, well, what's in the Y part? What letters are in the Y part? It's just going to be A's again, right?
Yeah.
Yeah. And in fact, I can copy a lot of this from above, so I don't have to redo it again. But come on, what's Y? Should I do that whole thing? Oh no, we got to do it a little bit differently, but we'll do it here. And then we'll figure it out. Because doing superscript and subscript in this thing is a pain. So, all right. All right. Y is going to be equal to A to the K, right?
Yep.
X is going to be A to the P. Let's just, sorry, but if I'm going to help you, it's going to, all right. X is, oh, fudge. I'm not going to do that anymore. I'm just going to reduce the slice of all. All right. So X is A to the P, where P is something, right? What's Z? Z is all of the other A's, right? So it's not just M, it's, there were 2 times, oops, 2 times MAs, right?
Yeah.
Minus the P minus the K, and then B to the, so, so that's what X, Y, and Z are, right?
Mm-hmm.
And so X, Y, Y, Z equals, let's see, we got one of them times 2 of these Y's. So let me paste and paste times Z, and Z is this whole nasty thing. Oops, I said M times 2 up here and 2 times M down here. I should probably make it the same so people don't freak out. M times 2. And this one is M times 2. All right, so that was my Y. And then I need my Z, which is this whole thing. All right. And what does that equal? Well, I got P minus P, and I got K minus K. So I think it's going to equal a to the m times 2 plus k. B to the m times 2, right? And does that have the same number of a's and b's?
No.
No. So again, we can say not in my language. Come here. Okay. But now we've got, what if we picked that? There's our string, and y is this, x is this, z is this, that whole x, y, y, z. All right. And then I say, heads up, sample PDFs of proofs on the class website. All right, there's this thing. So that's the outline that we had. But if you look on Canvas, you'll see I've got like more proofs, like, right? So, and here, right, y must equal, right? So this is a proof that odd palindromes, right? So this is palindromes are words that are the same forwards and backwards, like race car, and odd ones just have an odd number of letters, right?
Yeah.
And so I have this proof in there, and it's the same exact outline. And I have another proof in there, it's the same exact outline. And I have another proof in, right? So I have a whole bunch on. And in fact, I did a couple of different versions of these that are on Canvas so that you can see what's going on there. And what else did I want to show you? What else did I want to tell you? I think that's it.